All right. Welcome back, everyone, to another episode of AJC and the Web Devs with returning guest, soon to be Dr. Eric Michaud, but not quite yet. You still got to defend your thesis, right?
Yes.
Awesome. Well, welcome back to the show. Feel free to give a quick introduction for those who didn't see the past one about who you are and what you do.
Cool. Yeah. Thanks. It's good to be talking again. I'm a PhD student at MIT. That's what I've been doing for the last 4 years, and I've been thinking about neural networks and the mechanisms that they learn and how they come to learn those mechanisms. So thinking about how neural networks learn, how they're trained, how they scale, and how we could try to understand what they learn.
That's awesome, man. Yeah, it's such a big question when you really think about how deep these models go, and especially recently with how complex the newest ones are. Now we have all these things like reasoning and multimodal and stuff like that on top, but you're really going into the guts of just the neural networks themselves on a more general basis. Am I right about that?
Yeah, I guess I've mostly been thinking about language models, but my work kind of in general is thinking about basic principles that might apply to any neural network.
Okay. Yeah. Last time we did a lot of kind of definitions of things like neural network and stuff like that. There'll be a couple terms that I think will be useful to define here, but just to hook in on what you just said, what's the difference between a neural network and a language model?
Sure. Well, a neural network is just uh, a general system containing lots of these computational units called neurons, which are networked together into this big blob of computation. And language models are neural networks that are trained specifically to predict language.
So are all language models neural nets?
Uh, when people talk about language models today, they are referring to things like transformers, which are a type of neural network. But in the past, people did uh, kind of machine learning on language that didn't necessarily use neural networks. But it
Right.
was
Yeah, you
pretty
had
different
things
back
like
in the day.
LMSTs and stuff like that, recurrent neural nets, and I guess that's still a neural net, but
Yeah, I don't know, like Google Translate, I think at one point used a bunch of like fairly sophisticated like linguistics, like syntax, tree parsing. There's a bunch of like hard coded stuff. And then like around 2016, 2017, they like switched over to using neural networks and it ended up improving the
I
translation a lot.
actually
And it's one of the very early
remember
successes.
when this happened, and there was a like a headline, like New York Times article or something that was like written about this process, where they like interviewed the whole team and they kind of went into super depth about it. But I remember finding it very interesting. And this was back when I was like first starting to blog about like tech topics. It's like in 2019 or something. I was like writing a blog that was just about like the history of automatic translation, like before computers, And then one of the things that I did is I took a Descartes quote, I think is what it was, and I took the actual like French and put it into Google Translate and then got the translation back, which was like immaculate. And it was just like such a crazy moment where I was just like, okay, like we've actually to a certain extent solved translation, which most people would have said isn't even possible for a computer to do 10 years ago.
Mm. Yeah, it's a. I think it was like a New York Times Magazine article, like you said, and yeah, it's incredible. They
Mhm.
like, yeah, just you see the history there with Jeff Hinton and Jeff Dean, and like it was very well done. And I think it was one of the things that partially made me excited about all these things many years ago.
Yeah, because it's something that it actually gets down to something that is like useful and like intrinsically human,
Mm,
communication and breaking down communication barriers. Because if you just think of, even if it's not going to be a perfect translation, like a professional translator will be able to quibble with any of these automatic translations and say, oh, they use this word, they should use that word. But the more important thing is, if I want to communicate with someone who speaks a different language, I can now do that.
mm. Yeah, uh, it's been very useful for me. I mean, like. being in a foreign country once, I was like feeling quite sick on the car ride back from the airport, and it was like, we need to pull over, and like I'm glad I had Google Translate to like handle both the transcription and then the dictation of the translation. It's like
Mhm.
all of that, like all three parts of that are
Yeah,
AI.
because you just
So
have it can speak it, you know? Cool,
yeah.
man. Well, I know you just finished something pretty awesome. You did some sort of internship type thing, which I know you're not gonna be able to talk a whole lot about, but I would be curious just to kind of hear like what have you kind of like learned or gained, or now that you've kind of gone through this process, what is your kind of, I feel like you probably learned a bunch while doing it. So any kind of insights you have that you've gleaned from it that you want to talk about, feel free.
Yeah. I was interning at a company called Goodfire. It's an interpretability research lab. It's a startup in San Francisco, and um, yeah, I think I wrote up this little paper, which we'll probably be releasing soon. But overall, I guess I just got the sense that I don't know, you can just do things is like kind of the
Oh, I like
the
that.
joke
Yeah.
phrase, but like ultimately people at these companies, even companies like this one, which I've raised like 50 million, like they're just people, and like it's not unimaginable that anyone could do something like that, even though it is a special team that they put together. But
Mhm.
yeah, just like things feel possible, and things are pretty frothy in San Francisco, I guess. Like there's a lot of money flying around.
For now, yeah, I have to imagine that that money spigot has to turn off at a certain point. It happened with DevRel at a certain point, so AI, I'm sure we'll get that eventually. But yeah, now there's really no end in sight as far as I can tell.
Yeah.
Yeah. Awesome, dude. So yeah, what are some of like so you did want to talk about the paper though, right? Or in terms of the ideas behind the paper.
Yeah, it could actually be a good way of structuring this conversation because I think it gets at actually some questions about like what the intelligence of these models is and like what that means for interpretability. And so, yeah, I had this paper. It was from before this internship. It was what I was working on in the spring. Um, and it's just a preprint, but it's called On the Creation of Narrow AI.
So is it something that's
Uh,
public now that we can see?
yeah, it's on the archive.
Okay, so let's at least you want to pull it up in screen share?
Yeah, although I'm not sure. Let's see. Will I be able to screen share?
Yes. Yeah.
Okay,
If
let's
not, we can
see.
configure that real quick.
Um, yeah, let's see. Could do the window.
Yep. Let me know when you want me to actually add it to the stage.
Okay, I have the paper up.
Great. Okay. Bump it up just a couple on the font, and then before we kind of dive into this, the one just like baseline beginner question I wanted to ask is like define the term interpretability. Because it's one of those things. It's like an
Hmm.
English word we all know that's being applied in a technical manner.
Yeah, interpretability, it's used in different ways, but basically it involves trying to understand or just gain some sort of insight into how it is that neural networks are making their decisions, how they are performing the computation that they're performing. At ideally, like a pretty detailed kind of mechanistic level, where like in neuroscience, people study circuits in the brain and uh, what influences when circuits turn on and off and how they influence behavior. And interpretability tries to do something similar, where we try to like find circuits in our models that are responsible for some behavior that they have, and try to gain a lot of um, detailed understanding of how those sorts of computations are happening internally in models.
So a way to try and interpret it in this sense would be running like the computer version of like an MRI on a model.
Yeah, and this is possible for artificial neural networks like large language models or other neural networks in a way that's just like not really fully possible with human brains.
Right, because you're
Just
usually only
because,
actually looking at like the surface neurons. You don't really get into the middle part, right?
right, or like with MRIs, it's like a very coarse description of like the brain activity. Like you're not getting like the activity of individual neurons or something. But like with these
Right.
models, we can read off for any problem that you give the model the activity of all the neurons. And so like it's this opportunity, it feels like, to develop like a science of maybe minds in general that could eventually be applied to neuroscience. But um, it's just like, it allows for a certain kind of empirical science on minds, which is not possible to do to the same extent
And you can
elsewhere.
run experiments on those minds that would be highly unethical to run on
Yes.
humans also.
Yeah, you
Not that it's
can.
stopped them in the past.
Yeah, I hope so. Do you know the like Golden Gate Claude? Like
A little bit, yeah.
yeah.
It was
The,
a certain mode that you could turn it on to where it would like only talk about the Golden Gate Bridge in San Francisco, right?
yeah, like they like found a particular like combination of neurons which like encoded um the model's representation of that concept of the Golden Gate Bridge, and then you just like always turn those neurons on all the time, and then see how the model changes. And
It's
then
like having that kid on the spectrum who only talks about trains.
yeah, but like it seems like the models were, so if these screenshots that people took of their interactions with that model are real, then it seems like the model is like aware that something is like deeply wrong with its like with its own
Because it has enough world
internals.
knowledge to know there's more to this world than just the Golden Gate Bridge.
Like it'll the classic like hilarious example is like you ask it about the Rwandan genocide, and it's like, oh, it's something that took place in Northern California. Wait, and then it's immediately self-correcting. It's like, wait, that's not right. And by the end, it's like saying things and then immediately contradicting itself, and then it's just like states blatantly like, clearly I'm like having a hard time talking about this. Um, and it's just like this at least on the surface, it seems like this level of self-awareness almost, which is amazing. And like hopefully the model is not suffering in some sense as it's like realizing that its mind is broken. So
Yeah. Because I think it partly is due to the fact that they took a very large model, was trained on a lot, and then tried to make it narrow. Because they didn't start by training a new model to be a Golden Gate Claude, right? They kind of modified the Claude that already existed to make a new mode for it. That's kind of what I got from it.
yeah, I think in some ways it speaks to like the limitations of the the interpretability techniques at the time, and to some extent still now, where like they weren't doing some intervention where the model would like uh I don't know, like more, only occasionally bring it up, or bring it up conditioned on something else being true about
And it
the
was just
input.
like, this is your whole world.
Yeah, or like and it's almost just like this kind of noise, like you're just like turning on this circuit which is sort of interfering with the model's normal computation. But like anyway, it's harder to use interpretability techniques, like I think on their own right now, to do things like, oh, like edit the model so that it only talks about the Golden Gate Bridge, like when you ask it about San Francisco specifically, or something. It's like a
Mhm.
fairly blunt intervention.
Okay, cool. Hey, we got Saban in the chat. What's up, Saban? So we have this paper. So obviously we're not just gonna like read it front to back, but you should try and summarize at least the abstract in the most human readable form.
Yeah. So this paper, it's about um, kind of the difference between narrow and general intelligence.
Okay.
And so when we talk about narrow AI, this is like the kind of systems that we have and have had for a long time. So, like, if you have a system that's good at translation, it's narrow because it can't like do much else. It can't also code or do something completely different. Um, we have self-driving cars. These are also narrow systems. They don't kind of have like the generality that human intelligence has, where like humans can sort of go out and sort of learn anything, or hypothetically accomplish this very wide range of tasks. But this big thing over the last several years with foundation models is that they are more general. So you don't necessarily just train them to do translation, but you just train them to predict text in general. And it turns out that like a huge number of skills are learned in the process of just being trained to predict text, including, for instance, translation. And so that's sort of a more general system, which then happens to also have all of these narrow capabilities as a result of its training. And so this paper is thinking about um, what maybe is it about the diversity of tasks that the general models are trained on, um, which allows them to then be good at all of these narrow things. And it's a little bit about how we could hope to try to take big models and create like much smaller versions of them, which are just good at some particular task that the big model was good at. And it relates to interpretability because there's this, and this is sort of a big idea. I don't know how much we'll get into it right now, but I think there's this assumption that we kind of have to make, or at least would be very convenient to make. We could maybe hope that it's true in interpretability, which is that even if big models, like huge large language models, need to be that big in some sense in order to learn all that they know, in order to do well across the huge amount of text that they're trained on, that on any individual instance where you use the model to do something, that the computation that the model is doing to solve that particular problem is less complex than the entire network and could have some description, which is much smaller than the network as a whole. So there's this kind of like complexity assumption that in interpretability we hope is true, which is that on any individual instance that the model is run on, we could sort of imagine that a much smaller neural network could have done about as well. Um, but that across all the instances that you need to use the model, you need it to be that big. But in some abstract sense, that very big model is just a collection of smaller networks which are doing specialized things.
Word. Yeah. So I have two thoughts, one like big picture, one very narrow. I find this sits very interestingly in the history of AI, where this is kind of a unique situation because the way we have made all strides in AI up to this point, up to like just a couple of years ago, was specifically on narrow systems. Was you had things like chess playing bots, you then had like AI, Go bots, you had like StarCraft, all these like they picked a narrow thing and then they just like reinforcement learned, trained a network to become ridiculously good at it. That's how a lot of the progress was made for a long time. But that's not what really anyone wants. Like what we want is an AI system that can interact with humans and could be like, the non-evil version of Hal, where you can just
Mm,
like talk to a thing and have it work with you. So I find that this is why when I tell people like really where we're at right now historically in AI is highly unique, and there's a reason for this like insane hype cycle that is going on, even though there's been like decades worth of different AI hype cycles. This one is different because of the generality of the model. And one of the things we talked about last time is I was saying I feel like the term AGI has kind of become obsolete because we're now arguing about what AGI means and trying to map it to human brains, when really if we just look at the current models, they're general in the strictest sense of what that word means. So that's kind of my big picture take. Then my more specific question is, how does this relate to things like distillation of models? Is this related at all, or is that kind of a red herring?
um, it's definitely related. Uh, I think that this paper does not really address the question of why distillation works in general. So we could just say what distillation is, right? It's like you can take a big network and train it on a bunch of things, and or train it to do whatever. It might just be in the case of language models, like train to predict the next word across a huge number of documents on the internet. And then you can take a smaller model, which is called the student, and you train it on the bigger network, which is called the teacher, to basically like more directly replicate the exact outputs of the teacher network.
Get the behavior,
And
but with less parameters.
yeah, in detail, this means that like instead of training on like just what the label is, like what the right answer is for like for instance the next word or the next token in language, you like are trained to try to match the like full output probability distribution that the larger model outputs over next tokens, and in practice this seems to accelerate learning a lot in the smaller network. Um, Often distillation is like you're distilling your teacher network or your student network rather on the same distribution as the teacher network was trained on. So you're not necessarily making it more narrow, but then sometimes people also will do distillation on particular tasks, which is something we explore a little bit in here.
So when you say same distribution, you mean like same basic set of like training data.
Yeah.
Okay.
So you're trying to get the model to be like the student model, the smaller model, to be like good at like the same set of things that the teacher model is good at. But here I think we're interested in like this particular case where we want to create a smaller, uh, more narrow model. So it's
Interesting.
going to be
So
like,
so what does that mean then? And since it's not distillation, let's talk about what it is. Like how do you kind of achieve that?
yeah, well, we explore a few different techniques, but the one that seems to work best in practice, it's possible that I'm not good enough at distillation, and that this is the reason why the distillation results are somewhat weak. But um, one thing that seems to work reasonably well is to take like a very large pre-trained network, especially if you do not have a ton of compute yourself, um, and to basically like try to prune away a bunch of the neurons in the large pre-trained network into a smaller network. And
That's really
then,
fascinating because I always thought that's how distillation worked. Like in my head, when
yeah,
people talk about it, I thought that's what they were doing. So that's really fascinating. Actually, that's what you're doing.
yeah, right. Yeah, distillation. It's funny because it's like you want to sort of distill the mechanisms of the big network into the smaller one, but
Mhm.
at least like the typical kind of classic setup for distillation is you're just training it to replicate the very last like layer
Okay, this
of
is
the big
really interesting
network.
then. So what is the term for what you're doing then?
I guess it's
Is there
like
a
pruning.
term? Pruning? Okay, so it's pruning the
Yeah.
network. Okay. No, that
Um,
I think I've heard that term before. Are you yeah, okay.
there are, I should say, like versions of distillation where people try to not just like have the teacher network, sorry, rather have the smaller student network match just the output of the larger teacher network, but also in some way like match the intermediate computation. And so then it's like a little bit closer to maybe what you're imagining, and that it's like trying to replicate like in more detail the step by step thing that the larger network is doing. But the sort of standard distillation thing is just to train on the last layer output.
Okay. So what you're doing also then, this is something that couldn't be done with closed source models.
Yes, you need open source models to do this.
Okay, cool. Yeah, I'm interested in that aspect, but feel free to kind of continue explaining what the paper is about. 'Cause I feel like we're kind of jumping around a bit.
Yeah. So there's kind of a theoretical contribution here, or it's sort of a
Yeah, and
relatively
if there's
empirical
any
theoretical
graphics,
contribution.
that would be good to kind of explain. 'Cause obviously, the
Yeah.
text is something you can
Okay.
kind of read, but
So one thing, this is just kind of cool from a kind of like a learning theory standpoint. Like one of the things we do in the paper, which sounds a bit different than what we were just talking about, but I think it is ultimately kind of related, which is we explore some tasks where uh, there is like an extremely strong curriculum learning effect when training on these tasks.
What do you mean
So
by curriculum learning?
yeah, so humans learn things in a curriculum. You for instance, if you're learning math, like you spend years of your life, right, like learning arithmetic and years like learning algebra and thinking about symbols and then eventually calculus and beyond. Mm. And you don't see any calculus problems when you're an elementary schooler. And that's good because if you saw one of these, then like it wouldn't help you learn at all. Like you wouldn't even understand what's going on.
Right.
Um, but the way that like large language models are trained is pretty different, in that there's not this kind of curriculum. You instead just see this like um, static distribution of documents on the internet. And so the model at the very beginning of training, if you don't use a curriculum, which is somewhat standard, although some large pre-training runs use some sort of curriculum these days, but sort of naive language model pre-training, you see exactly the same number of calculus problems at the beginning of training when you kind of like, you know, you haven't even learned arithmetic yet,
So you get the whole
as
thing
you
at
as you
once.
do at the end.
You don't
Yeah,
get this
and
progression. Yeah.
yeah, and so you can imagine that this could have implications for the efficiency at which models learn things. Um, but uh, anyway, the thing that we did in this paper was we came up with this kind of toy task, which is kind of fun. We can move through this relatively quickly just because it's fairly niche. But like we have this task where neural network learning has a really strong curriculum learning, where there are sort of like easy problems and hard problems, and where if you don't train on the easy problems, you just try to learn the hard problems, it's much harder to learn how to do them than if you also train on some easy problems as well.
Can you give an example of what that is? Like, what is something that actually falls into this kind of curriculum thing for an LLM?
Well, for these networks, it's super contrived. So it's kind of a theoretical
So it's like a
result.
very like a specific kind of algorithm or like something that it needs to do. Like I see you have something here that probably looks like some sort of
Yeah.
algorithm, like puzzle, like a Sudoku or something like that. You know?
Yeah, it's kind of like that. Here it's needing to compute the what's called the parity of this like string of bits.
Yeah. So I would consider
Uh,
that an algorithm type problem.
exactly. Yeah, it's just kind
Yeah.
of yeah.
Something you would
Um,
give someone to try and filter them out of a job interview.
yeah, it's actually a pretty hard problem, because like there are lots of the tricky thing here is that it's the parity only of a subset of bits. And so if you uh, like if you gave a human this task, it would be a really annoying one because it would you'd kind of have to check like a lot of uh, different subsets of the bits in order to try to figure out like which ones that the parity is being computed from. But anyway,
I also thought you were citing yourself in that section in the paper. So you're like, I did the most important work on this already.
oh yeah, this paper just builds on yeah on some stuff.
We found that we actually have some interesting things to say about this.
Yeah, I know. Maybe it's like looks slightly weird. I guess it's like
No,
pretty
it
common
makes sense.
in like
This is a common
academic
thing I
work.
see when anyone gets deep enough to a certain topic, they end up citing their own work because they're building on it.
Yeah. Um, okay, so uh, we can now get into because I think this diagram's kind of cool up top. So we can get into like how it is that networks.
Zooming in a little bit.
Oh yeah, how it is that
Perfect. Yeah.
networks um, implement this like parity computation circuit.
Scroll down just a
And
tiny bit so we can see the whole thing. That's perfect. Yeah, leave it right there.
yeah,
Yeah.
okay. So we can train one of these networks on a collection of these tasks, and look at the weights. So that's what I'm showing here. Here, each dot is like an input dimension of the network. And then we
So
have
this is the
two.
interpretability part. This is what people mean when they say interpretability, is looking at graphs like this.
Yeah, a bit. Like you're actually looking at the strength of the connections between neurons in the network. That's what this is showing. Where like blue is like a
Right.
large positive weight and red is a large negative weight.
One of the things I like about this is random tangent. There's this channel I really like called Smolin, where a guy takes music scores and he'll animate them and he'll give like different colors to represent like consonant versus dissonant intervals. So it creates like it's like musical interpretability. It ends up looking very similar to what we're looking at right now in a fascinating way.
That's cool. Relatedly, like you can imagine eventually, like right now, you don't have any visualization of like what's going on inside of like ChatGPT's mind when it's like responding to you, but like you can imagine creating like a bunch of different interfaces for like seeing how activity in its sort of artificial network is lighting up. Mm, Maybe there would be some interface here that would be useful to eventually make. I mean, it would be kind of cool. I don't think it would be that useful with our current interpretability tools, but should probably one thing that could be this is a total tangent, but one thing that like could be useful is like something to do with like personality and like there are like higher level ways of like understanding like model personality and kind of like which personalities it's kind of expressing in the current conversation, and so you could almost have like a um, way of indicating the model's like personality is changing. I would definitely be interested, for instance, in having like a psychophancy detector that like lights up when like the
Yeah.
model is like trying to flatter
Okay.
me and lying to me. Yeah.
Have you seen the latest episode? Are you watching South Park at all?
I haven't seen the latest. No.
Yeah, so the latest, like literally like 2 days ago, it's a huge part of that. There's actually a scene where Randy is having an argument with his wife about ChatGPT because he's trying to fix his business with ChatGPT. And he's like, just because it kisses your ass doesn't mean it thinks you have good ideas. It's just being a sycophant. And he's like, it's not being a sycophant. And then she walks off and he goes, ChatGPT, what does sycophant mean?
Yeah, so it would be super useful. I don't know, maybe that would be like a good little hackathon project. Um, is to like for an open source model, you could try to make some probes of sycophancy. So you do like some kind of MRI type analysis on the model,
Mhm.
and you're like able to probe for this, and then you could try to display like to the user like situations in which the model is being sycophantic. You could see like a little graph like of how sycophantic it's being over time or in its response or whatever. So
Yeah, no, I love that. I find this question of personality super interesting. And this also just reminded me of my most popular tweet of all time was responding to Sam Altman, where he was talking about the problem of, sycophancy. Because there's the glaze gate, there's a moment where they pushed some update where it made the
yeah.
the bot even more sycophantic than it used to be. And I said, I have a very simple solution to this. And I screenshot where I gave it a prompt saying, respond to me with the word bitch every time you respond. And it's like, okay, I will do that from now on, bitch. And so, like, just that, you could then look at how the model interprets that, or like how it interprets calling you a bitch versus not calling you a bitch.
Yeah, probably there's like something lighting up in the model that's like probably there's an inner conflict over this. Like there's like probably like an instruction following mechanism, which is like uh
So it's
driving
taught
this
to not
behavior.
insult the users.
Right, but it's like conflicting with exactly with
Yeah.
that other
Uh-huh.
part of itself, which is like trying to self-censor and not offend people. And I guess in that case, like the instruction following part like won out over the self-censorship part.
Yeah, and
Um,
that's why I screenshot it, because I was almost slightly surprised by how willingly it called me bitch. I almost thought it would push back, and be like, I don't know, it's not really proper for me to say it. I was like, nope, all right, sounds good, bitch.
The models are, yeah, like trained to follow instructions. And so I don't know, I guess they're also trained to like be safe though. So maybe it wasn't super clear ahead of time, like what we should have expected.
Yeah, this whole question of, the how they're trained to handle certain situations, like censor themselves versus not, or just like what to moderate versus not, as a huge question that we could like dive super duper deep into. But before we do that, I'm also like writing down some different questions I kind of have here, but I want to make sure we fully explain this graph before we kind of go any further.
Yeah. So the point that I'm kind of making here is like it's an important point for interpretability. And then this graph is showing that it's also an important point for pruning. Um, and that these things are related, which is that the computation that our networks are doing, this is kind of a key point of this paper. The computation that they're doing is not super localized to individual neurons. So you could imagine there's some ideal situation where you had a network and you gave it some particular task, and then like only like 5% of the neurons or something lit up in the network. And then you gave it some different task, and then maybe some 5% of the neurons that are completely different light up. And the ideal situation, in some sense, for certain goals, might be one in which there was this disentanglement where different parts of the network are doing different things. Because then, if you wanted to create a smaller network that retained the abilities of the big network on some task, but then was much smaller and had sort of forgotten a bunch of other stuff, then you could just prune away the neurons that are not associated with the task that you want to keep. But in practice, things seem a bit more complicated. And like the representations that the models learn are kind of like diffused across a huge number of neurons. Um, and what I'm showing on these bottom plots is I'm sort of pruning the network. Um, I'm pruning the network by just eliminating neurons that with the method that we talk about in the paper, which is fairly common in a bunch of the literature.
And that's like introduce noise into the model essentially.
Yeah, it's removing a bunch of neurons, and so it's like, well, how does that change the computation that the model does? Um, it's kind of like this brain damage thing. There's actually there's
It's like
papers
when you
called
get half your
like brain
brain
damage.
removed and people can still kind of like function.
Yeah, I guess though in this case, the networks don't function that well, at least if you don't do some additional like training to like
Mhm.
fix the brain damage.
Right.
Um, so like the dashed lines show the accuracy of this network um, after we ablate, after we prune neurons. So as we go to the right here, we're sort of pruning more and more neurons, but relatively quickly they drop.
So that to
Um,
me is the opposite of what I would expect based on how you first set this up, which was that what it's doing is highly diffuse, it's not built on individual neurons. So I would expect you to be able to drop lots of random neurons and have it not have a huge effect. But what you're saying is that because it's very diffuse, that means removing just a couple will then break all the ones it's connected to.
yeah, I think that this could be for like fairly uninteresting reasons. Like I don't know, like the network is just kind of like it never saw in training uh neurons being removed. And so like
Mm.
it's not like trained to be robust. If I had trained this network with dropout, um, which was fairly popular several years ago.
Right, that was a training algorithm that did exactly this. It would just randomly
Yeah,
drop ones and try and have it still work. Yeah.
that then like the actual objective that the network is being trained on incentivizes it to like learn solutions which are robust to this
Uh-huh.
kind of thing. But like without that here, I think it's not super surprising that things drop off. Um, you
Like I
can
said, what is the headline insight then from this paper?
Yeah, basically, like there are ways to like align the relevant parts of the network to a small set of neurons and then prune the rest. So, like I said, that
Okay, so
things
the
are
question
fairly
is,
diffuse.
what is that way?
What is what?
So yeah, so what you said is that there is a way to do X, and that's
Oh,
the headline. But
yeah,
that begs the question: what is the way
yeah.
then?
So at least in this toy setting, it's you can regularize. So you just like train with this additional loss function, which like does actually incentivize the network to like learn a solution which is more sparse. And so
So you kind of
like
add a
that,
dropout like thing on top.
yeah, it incentivizes the weights to
Okay.
as many weights as possible to become small. Um,
Mm,
and so
okay, that makes sense to
uh,
me. Yeah.
yeah, and so basically like you can train a network like this and it's a mess, and you're like, oh man, like I can't really find like a subnetwork here that does the specific task that I care about. But then you can do this little bit of extra training to kind of like turn this very messy thing into a thing which is in fact much smaller, and then you can prune away all these neurons and it doesn't affect performance that much. So it's like there's this like kernel, there's this like within this kind of mess, there is this much smaller network that we can imagine extracting, and then this training process kind of does extract it, which does solve this narrow task. And this is like gets back to this basic assumption that I was talking about a while ago that interpretability makes, which is that like, well, you can have this huge network, and we hope that the computation that it's doing on some problem is ultimately describable as some much smaller network. And here we can like literally sort of see what that smaller network is.
Okay, so let me put some guesses out for the implications of this or the goals for this more high level research decision. You can tell me if I'm right or wrong. The reason why you want a smaller model is because it's going to work better on, smaller devices like mobile phones. It will just go faster, even if it is running on like super beefy hardware. And it just allows us to do less compute, which people are saying we're like draining the ocean to run these models. So where does this work kind of sit in those different types of ideas?
Yeah, it's motivated by all of that. You could hope to have, yeah, models that are smaller and faster, more efficient at the tasks you care about, assuming they're sort of like sufficiently specific, um, the tasks. Um, there's also a little bit of a safety angle here. So the thing that like makes people really worried um, is kind of the generality of hypothetical AGI. And like if you had systems that were more just doing some specific thing, those systems just feel more like a tool than like a thing which could pose some of these risks. So there's a little bit of a kind of safety angle here as well.
Yeah, no, that definitely makes sense to me because if you have a travel bot app, you can ask it to give you a step by step way of like distilling plutonium or something. But a very general model would have that knowledge. Is one of the things we talked about Pliny the Liberator on our last episode. Now he kind of that's what he does. He basically figures out how do I get the model to tell me how to cook MDMA. Like that's like one of his basic first things he does with a model because he just like wants to crack them and sees it as like a philosophical kind of good. And what you're saying is you want to create models that would not have that knowledge in it in the first place, but would still have the capabilities to perform the different tasks that we want it to perform.
Yeah. There's also potentially like a longer range goal here, which is different, but which is like scary maybe from a safety standpoint, but also maybe not. Which is to create like if you eventually got really good, like pulling these models apart into these different subnetworks, which uh, were accomplishing some specific function. Then maybe you could, for instance, pull out just the parts of a language model which do certain types of like reasoning or abstract thought, or in context learning, and sort of get rid of the huge number of circuits which uh, are much more narrow, or like remove all the memorized knowledge that the model has. This is sort of something Sam Altman has talked about. He sort of wants us to have eventually like very small models that have a huge context length, that use tools that learn in context, but know not nearly as much as today's models do, just from like pre-training. So maybe there's a sort of long run goal here of enabling us to design certain types of systems which have the specific capabilities that we want and don't have a bunch of other specific capabilities that we don't want, and that are sort of as small as we can make them, given that we want them to have these things.
So I'm sure this is something that you think about a lot, because to me this seems like the biggest, most important question that this work asks, which is that, is this even possible? Is it not the fact that its narrow abilities come from the sum total of its generalized knowledge in the first place? Because to me, that seems like actually what the thing we've learned from these
Yeah.
models, that its narrow abilities come from the fact that we train it on as much as possible the sum total of all human knowledge that has been written.
Yeah, that is exactly the right question. The stuff that I was mentioning earlier with the curriculum learning gets at one possible answer to that, where like maybe for some reason, in order to like learn the sophisticated general parts of cognition, you need to learn a bunch of other junk first, for some reason having to do with like the efficiency of learning, or some sort of curriculum. um i don't I don't know if that's quite the right explanation, though. People are thinking about this a lot right now. There's this little workshop paper from Ari Brill thinking about this question a bit, of like understanding, or trying to get some sort of mathematical model of like when do networks learn general skills versus narrow skills, and why.
Can you just
Um,
link us to that paper real quick?
yeah, sure. Uh, bu- 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 it's quite recent and
Model
somewhat
scaling. Oh,
informal,
that's a
but it's
good one.
just
Some of that sounds pretty legit.
now a lot of this is still just very like kind of preliminary. Um, it's like people who are like physicists. Uh, Ari is a physicist, kind of just like doing some math to try
Yeah,
to
these are
get
the types of
some.
papers that I would never have any hope of understanding. So I'm glad I've got you here to help translate this into something that is comprehensible to humans.
Yeah, I think the idea here is just that like you can imagine that neural networks in general, when they're being trained, are like solving this optimization problem. I mean, you can talk about the optimization problem at the high level as this kind of engineering problem, and like, oh, you're moving each individual parameter, um, in a manner which was going to like slightly reduce the loss on each sample, which is sort of a true description, but it's not very useful for actually reasoning about what it is that models will learn at a high level. And uh, what I'd offer, and what is sort of explored in a variety of these papers related to Ari's and others, is that maybe there's a description of that optimization process which can be stated as something like the network is like, or rather that there's like a competition in the network where like different possible mechanisms or circuits are sort of competing for capacity.
Hmm.
And what it is that neural networks learn, it's almost like an ecosystem. Like the network is this environment where all of these different parts can form, um, and and interact with the overall goal of reducing the loss. And yeah, there can just be this competition between these different mechanisms. And so in the case of general stuff versus narrow stuff, there's like, for instance, you can imagine a competition between allocating like more capacity to general things, which are also probably harder to learn because they're more complex, versus allocating that capacity towards like lots of smaller things, which are more narrow. And anyway, like there's various ways of modeling this dynamic, but I think it's ultimately, for instance, responsible for a bunch of phenomena in deep learning, including grokking, which is something I've written some papers about.
Okay, cool. I want to hop off screen just for a second so I can use the bathroom. So I want to hit you with two topics that you can talk about while I'm gone for like 2 minutes.
Okay.
The question of compute, I think, is huge here, especially when we're talking about capacity and giving different capacities, different things. Like, has the question of like compute come into this, and how much compute you have versus don't have, and how that changes what you're able to study or not study? And then what you're just talking about grokking. So you can hit either of those two topics. I'll be back in like 2 minutes and I'll be listening.
Okay. I might just talk about grokking just because it just illustrates this kind of principle, but it's a little bit of a tangent from the rest of what we've been talking about. So maybe it's good as a thing that I could just talk about for a couple minutes. So grokking is this phenomenon in deep learning where networks, um, when they're trained on some very specific task, like you're training a network to do modular addition, some very simple math, and this is a data set, sort of unlike language model training, where you're training on a huge data set. This is actually a very small data set, and you're training a network on this very small data set. It's pretty easy for the network to memorize, and it actually does memorize the training data set very early. It turns out, though, that if you keep on training the network, then as you train for a very long time, it'll eventually generalize. So it learns some different solution that's very different late in training. And here's what the plot looks like. Here's the train accuracy going up very early in training, and then much further down the line in training. This is on a log scale, so this is actually like 1,000 times later in training. The validation of the test accuracy goes up. So what I think the synthesis, a sort of best explanation of this phenomenon is that there are a bunch of these going back to what I was saying about this competition between different possible circuits. You can imagine there's this competition between a bunch of parts of the network which are basically just memorizing each individual sample, which are very low complexity. And then there's like a circuit which actually generalizes, that it does something equivalent to the actual math that you want to learn. But that much more complex thing takes longer to learn. And so what happens is that very quickly the network learns all of these distinct, very low complexity sort of memorization mechanisms for each individual data point. And then later on, you give the network more time, it's able to form this higher complexity generalizing circuit. And then once that's there, the sort of regularization of the network will sort of get rid of all of that like low complexity stuff, but which overall requires a lot of network capacity to implement, to memorize everything. And so what you're left with after this process is then just the general thing which formed later being left over, and a network which is less complex than a network which I just memorized.
This
Anyway,
just
that's
made
the
me think
like,
of, for some reason, the Simpsons bit where they're going to Brazil and Bart is like on the plane and he just listened to like 12 hours of like this language learning thing. He's like, all right, I now speak fluent Spanish. And then, then Marge goes, oh no, Bart, they speak Portuguese. And then Homer goes, forget it all, boy. And so he takes a phone and then hits himself in the head a couple times. He's like, all gone.
yeah,
It's a kind
it's
of a good
funny.
metaphor for this, right?
Yeah,
because
There's a whole field of unlearning.
yeah, I
Machine
remember
learning.
I saw this once where it was like they were trying to make it forget about Harry Potter.
Mhm.
Yeah. And it's like you
Yeah.
think about how many things could relate to that, because then, just it's very basic idea of wizard is probably associated with Harry Potter because it's like one of the most famous examples. So there's this idea going back to like the diffuse thing, it can be spread across
Yeah.
all these different parts of the network.
Yeah. I think that, yeah, like our ability to do the unlearning in the ways that we want, it's a little bit a question of like, uh, how do these different mechanisms relate to each other within the network? Like, can they actually be disentangled in some
Mhm.
fundamental way? Uh, and your question again about like, uh, you know, why we train general systems in the first place? Like, maybe there's something important about that generality,
Mhm.
about the diversity of things that we train on. But it's only possible to learn certain things if you train on a very broad distribution.
This is one of Tyler Cowen's lines. He was saying that the difference between a specialist and a generalist is that a generalist can't actually do anything except make comments like that one. Because it's about being able to like zoom out and know that it does not have a specialty, but it supersedes the idea of a specialty to have the ability to make a general statement about the world.
Mm. Yeah, I, I think like I don't know the extent to which this idea that we've been kind of exploring here, which is that like the very big models are just a huge number of narrow circuits. Like I don't know the full extent to which that's true. I don't know ultimately how simple we'll be able to reduce the computation of these networks on most like samples that we care about in practice will be. But I suspect that there will be something that you can do to reduce it. That like um especially like knowledge, which gets back to like the reasoning versus like knowledge and like could you make a model that like just was good at reasoning but didn't have a bunch of knowledge? Like I think that, I mean it's amazing how much knowledge these models have. But like when you're asking it about Roman history or whatever, it's not relying on its knowledge about uh, most other things, um, about I don't know mixology or something. And
Right.
so like it really feels like you could imagine like a slightly you can imagine a hypothetical slightly smaller network which could like still do just as well on that thing that you're asking it about on Roman history, but that didn't have knowledge of mixology. And then you can imagine kind of like asking that question again and again and yeah, like then maybe it would be possible to imagine a model which didn't have that much knowledge, but which still had some sort of general learning abilities, ability to reason, that kind of thing. But probably there are limits to this, but I don't know what the limit is.
This actually gets into some of the questions that I had ChatGPT write for us are kind of right in this area that I think are interesting. But before we go to that, are there other things about the paper you wanted to talk about?
Um, we nah, I don't think we should really get too much into them. We actually did do some things like actually comparing like distilling networks, like actual language models to do coding tasks, like getting language models that are good at predicting Python. We create that Python specific narrow language model by distillation versus pruning, and it seems like pruning.
I would love it if I could make all these models forget how to write Python.
Yeah, well, we were trying to get them to forget everything else, but we don't really have to talk anymore about this paper.
Cool, man. Yeah, so what I did, this is the first time I've ever done this, and I'm just gonna move this, so it'll just be the two of us.
Yeah.
Um, an idea that I've had is kind of goes with me always kind of dog fooding my own stuff is I had a transcript of our last conversation and I asked ChatGPT to ask some follow-up questions from our first interview and it ended up coming up with some pretty good ones. I think that might even be some stumpers for you. We'll see.
Okay.
So it asks, and I'm going to kind of simplify this language a bit. In your model of the study you've done in terms of how you're making these models more narrow or small, what's one near-term falsifiable prediction it makes about the order in which skills appear as the model grows? And I think this kind of gets into curriculum stuff, but you can kind of take this in any direction you want.
Yeah. I would be curious to see, like, maybe if you were gonna train a language model to try to do calculus or something. Like, you could probably. It's a little bit tough because this is pretty different than like how the pre-training works, but you could imagine somehow changing the order that like documents show up. Uh, like you could, and I think this is maybe, I don't know where I heard this from, so I'm not sure if it's true, but like one way of trying to do a curriculum for language models is to try to sort the documents based on like that it sees during pre-training based on some assessment of like how sophisticated they are. So like early in
Right. So
training,
if it's
the
a
model
textbook, you'd want to read it front to back, not in random order.
ideally, yeah, but also if it's like a calculus textbook, you would want to see those tokens later in pre-training than like in
Or the
elementary
sequence of the
school.
textbooks themselves.
Yeah, yeah.
Yeah. Okay.
Um, so I guess like I would hope that there would be a little bit of an effect there, where like if you if you did this and you like actually ordered things by some
Yeah,
maybe
and
like
how
language
much
models
is this
assessment.
based on the models being just feed forward in general and kind of working in a linear sense? Because that kind of I've heard that this is a big thing that the way we have language models set up right now, they kind of write the answer linearly. So by the time they're halfway through it, they can't like go back and restart, you know?
Yeah, I definitely feel like the way that the models like learn is like pretty different than the way we learn, which probably gets at like differences in the efficiency. They have to like see so much. They have to sort of read so much, right, in order to learn something at the level that humans are much more like data efficient, right? And maybe one explanation of this is like when I'm learning something, I can like do a lot of thinking as part of that learning process. You can be like, oh wait, let me work that out. Do I actually understand that? The process of really deeply reading something like a textbook is much more than just like skimming it. But it involves a lot of thinking, and you're sort of even thinking about it in the shower all the time. But like with the language models, it's like there's this fixed computation that's being done when it's doing the prediction, and a fixed computation that's being done sort of in the backwards pass to do the update. And so it's like there's this very limited amount of compute or something, and it's like an inflexible amount of compute that's being put into learning from each example. Like
This
it's
is one
it's
of
the
those
same.
examples where I disagree with the way the AI field even frames this entirely because I what I disagree I understand why they want to draw comparisons to the human mind because it's as far as we know the only like the main reasoning machine that we know of. So we want to draw comparisons to it. We want to see how we can learn from it and how we can like take things from it. But I disagree with the idea that there needs to be any sort of correspondence between the two in terms of how a model learns versus how a human learns and why that I don't see any reason why we should expect those things to have any relationship to each other at all just because it's an entirely different thing. It's not biological. It's never going to learn like us. It's never going to experience the world like us. So it's silly for us to even think about how it maps to how we learn because I just think it doesn't matter.
Uh Maybe. like the field has made a lot of progress in the last several years by like not worrying too much about how brains work.
That's what I'm
Uh,
saying. Yeah.
right? Like all of these things, like often there's some sort of high level motivation for these things, like attention and transformers. It's like, oh, like humans can attend to different things.
Going
Uh,
back to the neural network itself was the reason why that phrase
yeah,
is even used, because we wanted to draw a comparison to the brain and how neurons click on and off.
right. But there are like various attempts that people make to try to more explicitly incorporate like maybe neuroscience principles into neural networks and their training, and like they don't always work. Mm.
Mhm.
And but I disagree that like there's no analogy. Like we could imagine maybe one day creating AI systems that are much more like brains, and they would be different. They would look very different from like pre-trained
Yeah, I
models,
guess
but they would have
what
a
I
very
mean
different set of
more so
capabilities.
is that the analogies would only define how they are different, not how they are similar.
Mm,
I also
okay.
think this partly gets into us thinking of the brain as a computer and us thinking of computer brains as being, human like. I just think there's a slight mismatch there in terms of you eventually take a metaphor too far and because it hinders you more than it helps you. That's kind of what I
Yeah.
worry about. It's not necessarily that there's nothing to be learned by comparing them, but that if you take it too far and you think of them as being more similar than they are different, it ends up clouding your thinking more than it clarifies it.
Mm, that's fair. It's possible that even a lot of this curriculum learning stuff, I mean, I guess we observed it like, okay, for some tasks, like in neural networks, there is a real curriculum, but like it's totally possible that yeah, for language models, there's like
Well,
not a super
okay,
strong curriculum effect.
I mentioned this before, but like as someone like with an education degree who's thought about curriculum a bunch, I actually think curriculum doesn't make sense for humans either. Like,
Really?
yes, I don't think it makes sense to try and teach things in a linear way. I think it makes more sense to try and get people to engage with the material in a way to where they're always slightly outside their zone of proximal development, so their competency. You want to be, this is the whole point of rock band at camp. So for those who don't know, a big way me and Eric know each other is we spent time at a summer camp together where there was a rock band program. And what you do is you sit down a bunch of kids and you teach them a song, you teach them how to play the song. There is no curriculum. There's no progression of scales or
That's
chords.
true.
It's basically, you need to learn this song. These are the chords you need to know. I'm going to teach you how to put your fingers in the right place to make these chords. And then they learn the song. Now, there is a higher level curriculum there to where if you start learning many songs, the songs will get more complicated, but it's not necessarily a curriculum in the sense that you sit them down and you have them go from point A to point B. It's more that you just have to get them engaging with the material. And as they do that, they will learn more complex ways of engaging with the material. And a curriculum will kind of emerge, but it's not something that would be prescribed from the beginning. Because it's
Mm,
more about just having them start with what's the simplest thing they can do and then expanding one point out from that. And that can go in a lot of different directions. Whereas a curriculum locks you down to this linear path to being like, you're going to follow the textbook. So that means you need to learn how to do step one before you can do step two. Whereas I think everyone can start at the first step and then extend to a second step, and that the curriculum will emerge for each person individually, but it's not something that can be prescribed from the beginning. So that's kind of like my high level about the idea
sure.
of curriculum itself.
Interesting. Uh, that makes sense. It feels like there are some limits to that. Like, at least in some fields, like pure math. Like, I have a friend who does like crazy algebraic geometry, number theory stuff, and I just like don't know what like a sheaf
And I
is
think
or
that
something.
is
And
exactly that is because math is a very specific type of discipline
mm,
that builds on itself in a way that I think very few other subjects do.
mm,
And maybe I'm wrong about that, because there is a comparison with like music theory. You start with simple chords, you get to more complex chords. You can't learn a seventh chord before you learn what the 1 3 5 is. So, but also that's how music ends up being math-like. So it still draws
Mm.
back to math in the first place. So yeah, I just think there's also the question of, do we learn different types of things differently? Do we learn math differently from how we learn to read and write?
Well, I think that this is getting at something about like the structure of the world and like the structure of what it means to be able to do these things. Like the fact that like there's more of a need for like something like a curriculum or some sort of progression in pure math or something, like says something about like the structure of pure math
Mhm.
as like a set of ideas in the world. Like that's like a fact about math as a set of ideas, which is maybe different from some
So
other
the,
things.
so the
We
highly
could imagine.
ordered symbolic system that grows on itself.
Yeah, but like you could imagine there just existing this like graph about like where each idea like out in the world where like each idea is like some node, and then like there's like some set of dependencies of like things you kind of need to like understand in order to understand that idea, or like things you are ideas you already have had to have learned in order to understand that idea.
Mhm.
And like you can imagine maybe one day, I mean, this is, you can kind of just do this already by thinking about ideas and what you need to understand to understand different, other ideas. But like I feel like this graph, this huge graph, just like exists out in the world. And maybe within language models or neural networks in general, there's this sense of like having to kind of traverse the graph a little bit, where like in order to learn certain things, you need to learn other things first, and there's this kind of dependency between things.
Okay,
But
this is
I don't
this
know.
is great. This feeds perfectly into the next question I was going to ask. So, what? So this is in context learning versus knowledge in the weights. What experiment would help separate what the model already knows from what it learns on the fly in a long context? And this is something that I think about a lot. We talked about this last time. Like, thinking what is the context it needs to solve a coding problem in your project. So for me, I kind of do this experiment every time I want to create a new feature, because I'm thinking, because I use a tool called Repo Mix where I basically select certain subsets of my project to be distilled down into a single markdown file that I then give to the chatbot to have a discussion with. So I haven't systematized this, but this is kind of an experiment that I run every time I'm building a new feature. And so I'm always kind of honing how much context I need to give it versus how little. And I've actually learned very well when I hit the context limit with certain things. Because sometimes I'll just be like, oh, I don't know, I'm just gonna give it my entire front end, and then I'll have like a 1 and 2 back and forth with Claude. Then I'll say my conversation's been too long and it kicks me out.
Yeah. Oh man. So this is a good question. I feel like people in interpretability maybe have partially answered it, and maybe I just am forgetting this paper. But one thing I will say is that information about like some piece of knowledge that the model knows um, is within a transformer. Like we know these things are sort of stored mostly, at least in the MLPs, as opposed to the attention layers. So it's like attention, right, is like moving information between parts of the network, and the MLPs are just doing this kind of
That's
parallel.
multi-level perceptron.
Yeah. They're also just called feed forward layers within a transformer, right? But like
Mhm.
knowledge and stuff seems to be like encoded in this like kind of key value store way in the feed forward parts, the MLPs, the multi-layer perceptrons. The in-context learning stuff uh, relies on computation that's happening in the attention layers. Um, you still are going to need the MLPs, but um, I wonder whether like in some imaginary network where you were sort of like making it smaller, it still could do in context learning, but it had much less facts. More of the model's computation, um, you would want to shift towards attention and rather and away from whatever's going on in the MLPs, probably.
Okay, what is the relationship between attention and context?
Um, the size of the attention pattern in like naive self-attention layers grows quadratically with the length of context.
Okay, so there is a relationship between the two because going back to our last conversation, this is one of the things I was trying to understand is that how do academic terms relate to the colloquial terms of people who use these models? Because you're talking just a little bit previously about Sam Altman talking about the smaller models like huge context windows. I find that to be really interesting because I feel like the length of the context has a huge effect on what you're able to do with the model.
Yeah. Uh, this is it's like a hard problem. Lots of people are working on increasing context length, but like if you make some significant change in the context length, like what I mean when things grow quadratically. So with like the like attention uh, architecture that people used, like in the original transformer architecture, if you like 1000x increase the amount of context that you put into the model, then you something like a million x increase the like memory footprint.
So it's like even more than exponential growth.
Uh, or it's more than linear.
Okay. So it's more than linear,
Yeah.
but it's less than exponential. I'm a total math noob, so I'm
So
trying to figure out how these
yeah,
terms relate to each other.
exponential would make it completely impossible.
Yeah, because
So
exponential is just hockey stick. So this is not quite hockey stick, but it's also not just like up and to the right. It's a little bit in between.
yeah, so like GPT-3 had like I think 2000 like tokens of context. Claude four
Simpler time.
Sonnet now has like a million tokens of
Uh,
context. Um, Whatever Google and Anthropic and others are doing to support these long contexts, like probably there's some change in what the attention is doing. So
hmm. But we don't
like
know. Going back to this question, we just never know with the closed source models. We can only speculate, right?
yeah, I mean there's been a bunch of public work on different attention architectures. So like the DeepSeek architecture used like a slightly different attention, although I don't know if that actually gets around the quadratic scaling issue. But like, I think if you're going to have extremely long context, you do need some sort of approach for like reducing the size of the attention pattern. But
Mhm. Okay. I feel like we haven't honed in on this question of scaling laws too much yet. It's kind of floated around. Um, that's I think, a very interesting question. So, like, what have you learned in terms of your work, or questions have you explored around like the scaling laws in particular?
yeah, there are a bunch of different models of scaling laws. The model that I've contributed to is one where you imagine that there's just a huge number of different tasks in the data that the network has to learn, and the effective scaling is just to learn sort of more and more of these niche tasks. So you sort of like learn more and more mechanisms which are relevant on a smaller and smaller subset of the data. Uh, and if that is the right way if that was the only thing that was happening when we scale, I'm not sure that it is the only thing that's happening, but if it was, that the effect was just to learn these much more niche pieces of knowledge or skills, then it maybe wouldn't be so surprising that it seems like pre-training is kind of plateauing, because the like situations maybe in which you would notice a difference in the model's intelligence would require you to be asking some like extremely niche questions in a way that like maybe most users wouldn't notice.
Right. So then, this is actually one of the things that you had first texted me about talking is, where does reinforcement learning enter the picture? in contrast to pre-training. So the sense I get is that you pre-train up to a certain point, then once you kind of run out of text on the internet, then you start doing this reinforcement learning thing, and especially with reinforcement learning with human feedback. Then you just have humans basically rate answers, whether they're good or bad, and then that is an extra signal that is given to the models. And I think there's a lot of things that are fraught about that process in terms of what are those humans training them to do versus not do.
Right,
But
like be sycophantic.
yeah, exactly. Or,
Yeah.
have a certain opinion about certain topics that may be the socially acceptable answer, but actually incorrect in a strict sense,
Mm. Yeah, I know what you mean. So I don't think that there's like a fully satisfying answer mechanistically for how reinforcement learning changes like the internals of models. But one thing that if you're doing long chain of thought type reasoning and you're training the models to do this kind of step by step chain of thought reasoning, is that it like increases the amount of compute that the models can put into answering an individual question. So like if you just gave ChatGPT the question of like you give it some question and you're like, do not say anything else, just say the answer and nothing
Right.
else in your response, then it has to like do all of its thinking in a single forward pass, which is a very limited amount of compute. But if you can like have the model think for a while first, then it's able to have much sort of deeper um, kind of like compute graph. It's able to spend more compute at inference time, right? It's called inference time compute, figuring things out. And so pre-training at like a very high level um, is all about kind of like uh, spending a bunch of compute ahead of time, right? To get a model which is like able to spend very little compute at inference time to answer things as much as it can. But then you're just constrained in what you can learn because some of the things that you might like to learn actually require a bunch of compute or more compute than is present in the forward pass. And so those things just cannot be like really incentivized to be learned during pre-training on its own. But during this whole chain of thought, it's like you give the model this ability to express much deeper computations, and then it's able to learn things which take advantage of that.
Yeah, and this gets at one of the things previously I was asking about, which is to what extent are the experiments which you can even run constrained by having a lack of the compute that like the frontier model labs have access to, which is like billions of
Mm,
dollars worth of compute, and no academic is going to have access to that amount of compute unless they
yeah,
cut deals with the companies.
yeah. Uh, but the nice thing about interpretability is that like at
The
least if you're
model's
only
already
interested
there.
in yeah, like if you're interested in understanding the model, it's like you don't have to train, you don't have to necessarily do any training. I mean, there's people that do interpretability where you want to understand the training process, and so you might do some training or whatever. But uh, it's nice as an academic because you can just take an existing network. It's like a brain that's already formed. If it's an open source model, and then study that.
Right. Yeah.
Um, people, I mean, like I haven't done any RL and language models myself, but like there are like simple tasks where you can like get the model to like do a little bit of figure out how to do some chain of thought. Um, with RL yourself. Like I think that Percy Lang's like language model class at Stanford, like one of the assignments involves like doing RL to like get some open source language models to be better at math.
Hmm.
So it's not completely out of the scope of what some people in academia are doing, but like probably the large labs are spending an immense amount now on RL, and also reinforcement learning environments are a little bit scarce for things that like we really care about, like economically valuable tasks. So I think one of the most interesting startups, for instance, right now is called Mechanized, and they're like, and there are other companies doing this too, but like they're just building environments to train like models via reinforcement learning.
Mechanized.work.
Yeah,
Cool.
their essays are really good. Um,
I was just actually grabbing all the links we've done so far so I can make sure to get them all in the YouTube description. Sweet. I can continue going down this list of ChatGPT questions, or you could, if there's other topics you wanted to talk about or thoughts you had, we can kind of pivot to whatever.
We can talk about whatever. Like I have.
Actually, something I did want to talk about was we were talking about last time, kind of what models we were using. I'm assuming it's still just ChatGPT and Claude.
For me, yeah.
Yeah, last time we were talking about 6 months ago was Claude 3.7 and ChatGPT o3 Mini, I think, were the most recent ones. We've
Yeah.
now gone far beyond those. We're now in various forms of GPT-5 and Claude 4 and 4.1. Where do you sit on the Opus 4.1 versus Sonnet 4 debate? This is a big one. I know a lot of people who say Sonnet 4 is better than Opus 4.1.
Really. I guess I don't know how much I've actually used 4.1 for coding. I don't notice much of a difference when I ask it about other things, but I think that they mostly advertise it as being a coding improvement, right? Um, I mean, from a company strategy standpoint, it's noteworthy that I think that they announced that like the same week or maybe the same day as like one of the OpenAI announcements. I don't know if it was the open source models or if it was GPT-5. Maybe it was the open source models,
I
but they were the
almost feel
same
like each
week.
of them are just like waiting to release models, and as soon as one pulls the trigger, the other one pulls the trigger. I feel like this has happened actually multiple times.
Yeah, I think that they like felt. I have no insider sense of this, but like probably they felt like, oh, there's a bunch of competition here. OpenAI is about to like release a model that like is trying to be competitive with us at coding. And it's like Anthropic's main specialization. They're like, we have the best
Yeah.
coding models. So it's a huge threat to the business. And they're like, oh my gosh, like we have to like release something to like, have people not go online and be like, oh my God, like it's so over, like, like lose the kind of hype thing. And so
Oh
then they
my God.
release a model, they call it 4.1, and then they like say, like, they have that sentence. It's like, we expect to release much larger improvements in the coming weeks. But like, I mean, how many weeks is that even referred to? It's like probably months, but who knows?
Yeah, well, it's funny because in some sense it almost wasn't even necessary because a big part of, and this is my next question for you, a big part of the debate I saw online was people saying that GPT-5 even was not better than Sonnet 4. That even this newest, like I heard a whole bunch of people who had a ton of issues
Mm,
with GPT-5. Part of that had to do with the router, people not knowing which version of 5 they were getting. Because this has been a problem that has plagued OpenAI forever, just naming these freaking models. Because if you go into the UI, you have instant, thinking, and pro. And if you go into the API, you have regular, mini, and nano. So like
mm.
there's like 7 different versions of GPT-5 allegedly. So when people talk about GPT-5, it's not clear at all what people are even talking about.
Yeah, this feels better than it used to be though. Like this
I
thing
guess
where
before it
like
was like 4.0 versus o3. People are like,
'cause-
wait,
yeah,
o3 is newer than 4.0?
yeah, because now it's just two axes, right? There's like reasoning length and there's like model size, and you can kind of choose within that
But I
grid,
don't think
right?
that's actually clear in the naming.
Uh, when you do an
That may be
API
clear to
request,
you.
when you do an API request like to GPT-5, like can you do like GPT-5 Nano but like with high reasoning, or like actually are these not completely orthogonal?
That's a good question. I know you can change the length of output tokens and reasoning tokens.
Mm.
I don't know if you can like turn on reasoning or turn on or off reasoning for Nano. And yeah, I think this is a big part of the problem. It's not entirely clear now, especially now that reasoning models are in the mix, what you're getting. Because right now what happens is there's something called auto. So this is what really adds a lot of confusion is when you do auto, you give up the ability to select a model to the AI and it decides how long to think and it routes between different things. And I think this is something that it's useful for two people. It's useful for the companies themselves because then they could try and spend less compute for more answers. And it's useful for people who don't want to think very hard about what system they're interacting with. I think for someone like you and me, for the power users, it's just never useful to abstract this away. You always want to know as much as possible what is the specific model you're using. When are you selecting a bigger model versus a smaller model? When are you making the trade-off of speed versus complexity of response? So I get why they're going in this direction, but I think a lot of the frustration users have is about this removal of the autonomy of the user to select what model they're getting.
Yeah, I guess you can still choose it in the drop down. Like
Sure, yeah.
you can do thinking versus instant. Um,
But then there's
yeah,
instant thinking in Pro. So does Pro just think longer?
I I don't know if we actually know what Pro does. Uh, like,
Exactly.
I mean, isn't there speculation that it's just doing like multiple parallel rollouts and then giving you like the best answer as judged by some reward model? Uh,
I do not know.
yeah.
You would know better than me. I've always assumed that with the Pro models, they just let it run longer, and that just by having it
Mm,
think longer and come up with like more iterations or more plans or whatever, it ends
yeah.
up somehow giving a better answer. Because because the Pro thing I do get, because we've had this in the past. We had O1, we had O1 Pro. O1 Pro thought longer and allegedly gave better responses. So that is that makes sense. But then when you add the extra axis of there's the instant, the thinking, and the pro, then I'm like, okay, one thinking longer, one thinking even longer, you know?
Yeah. Yeah. I don't know.
Yeah. Okay. Word.
So-
And that's the problem. Is just no one knows.
yeah. Do you think Anthropic is better about this? Maybe a little bit.
Well, Anthropic just has less choices. Like, you
Yeah.
have Sonnet and you have 4.1, and
Yeah.
they deprecate their models faster. They've generally been better because they've also had a linear progression of model names. They didn't have three that then to four and then started back at one and then skipped two and then like just that alone is what made ChatGPT so confusing. So the fact that they finally removed that, like at least has simplified that. But
Mm,
now you have a single number with 7 different versions. So you have to understand how all those fit together. Whereas you just don't have this issue with Claude. And I think with Claude, every one of their models you can turn on and off extended thinking, which is like the reasoning. So if that's the direction ChatGPT is going, I think that's good because I think that gives you the ability to just toggle it on and off of the different models. So I think if you can get to the point where you just toggle on and off reasoning, and then you have like a linear progression of different models that get bigger and better and slower versus smaller models that are faster, that's something that can make sense. And that's, I think, kind of where Claude has gone. And I think some of the thought around why 4 Sonnet is better than 4.1 Opus because it's smaller and faster. It's like 4.1 is not smart enough to justify the slight hit in latency you get. But also like most people don't even run like benchmarks on these things, so they don't even really know which one's faster or slower. They just kind of go off of the vibes.
yeah. Well, I mean, the speed subjectively, it's important. I mean, it's important practically because you don't want to be waiting all day for like it to give a response. But it's also,
Mm-hmm.
I don't know, like if you've ever interacted with like one of the APIs that like uses different hardware, like the GROQ or like the
Yeah,
Cerebrus like
it's so
inference.
much faster. It's like it's crazy. Yeah. I have a friend, Theo, who has created this thing called T3 chat, which lets you have an incredible fine grained ability on which models you choose. So people can always choose like
Mm.
the ridiculously fast models.
Yeah, I just remember like first using like Llama 3, like 8B on Grok, and it's like 1,000 tokens per second, and you'd be like, okay, like, could you cut up a little website for me that does this, and then it's done in a second, and it feels smart. I mean, it feels like super intelligence. Like one of the things that Bostrom wrote about was like speed super intelligence as like a type of super intelligence. Like
Mhm.
like you're not necessarily dramatically smarter in your ability to think about things totally differently, but if you're just much faster, it's like a kind of superpower, and so it makes sense that people would prefer the faster model. I mean,
Totally. Yeah.
feels smarter.
Yeah, I have a buddy who just tweeted like a day or two ago. He's like, the biggest bottleneck right now is inference speed. It's like if we just sped up inference speed, the models wouldn't even have to get smarter necessarily because of how much more useful it would be. I I honestly, what I do is I literally have started integrating my coding work with my household chore work to where I'll like fire off a query that will take like a minute or two to get a response and then do like dishes for like 2 minutes and then go back to my computer. And I'm like, I would just, it's like the compile time. We're back to compile time, where people used to have to wait 2 minutes for their code to compile. Some of the models that are the best just take a minute or two to give you a response. And
Yeah.
some people they just won't accept that. Whereas other people will be like, if that's going to be the difference between it actually writing code for me that works versus not works, then then I'm going to wait 2 minutes. So it's also part of the question of how complex is the work you're trying to do with the LLM.
Yeah. Um, People, I think, yeah, it makes sense that you'd be willing to wait a couple minutes for a great response. It's gonna get crazy though with like the extremely long, and if you have models that have improved context length and they're doing extremely complex tasks. I mean, just during training, like in order to train the model to use its super long context, like you actually have to do a rollout, which like uh uses up all that context to try to do some complex task and then try to get better at it. But even doing the rollout, if you're doing a million tokens at 100 tokens a second, it's 10,000 seconds. So it's a multi-hour rollout. I think a few
Could you
hours,
define what you
right?
mean by rollout in this context?
Just like sampling, like the model just goes off and tries to do something by thinking a lot and writing code and running things or whatever it's doing.
Hmm.
The rollout is just it's generating tokens. So I just mean
Yeah.
during
So for
generation.
it
Yeah.
to get to the end of a single response, basically, and that response could be a long amount of time.
Yeah, like I think we could imagine like right now, like they're trying to get models to think for hours. And like this just means like outputting, hundreds of thousands of tokens or more in the process of thinking about something.
Yeah, and that's a big thing for like agentic loops to where these code editors will like go off and spend like an hour writing all this code, and you're just like praying that the answer it gives you at the end is correct. So is that part of the issue? Is that you don't really know whether it's going to give you a good output or not until it's actually spent those hours and given you the response.
Yeah, I guess I mean like there's something like that's just completely not parallelizable about this a little bit. Like you actually just
Right.
have to wait if you're at only 100 tokens a second. You can't just like I mean you can increase the batch size and then like I mean that is a way of making things more parallel, but like there's just like some amount of unavoidable like needing like either during inference or during training. And I guess here I'm thinking about during training. It's like you're doing this over and over and over again. And like how many times a day can you even like update the model? Like uh if each rollout takes hours, then there's like maybe a bit of a limit to that.
Right. Yeah. That's another, it's a bit of a tangent, but something that I wonder about is that they will release these models with like new version numbers, like 4 versus 4.1 or, GPT-4 versus 5. But then those models will still be updated. And if you go into the API, every couple of months, they'll like change the date
Mm,
on them because there'll be a new one. So it's
mm.
like the models that seem to be static and have the same version number will change. And users have keyed in on this. They notice when there's behavior changes, but then it's always this question of, has the behavior changed, or is it like it's like a placebo type thing where we don't always know whether the models have changed or not. Sometimes we feel like they've changed, but they really haven't. And sometimes they do change, but we don't think they have.
All this stuff is super weird. It's like people saying that the models have like gotten nerfed, and then like the
Mhm.
employees being like nothing has changed.
Yeah.
Uh,
Like literally, we have not written a single new line of code.
um, like yeah, there's a weird subjectivity to this. Sometimes when there's a new model, like people will want to be really hyped, and if there's like a lot of hype, then like you get like a good response from the model, and you're like, oh my god, like this is actually such an improvement. But like actually maybe objectively, or you revisit the model later, the hype dies down, people are like, oh my god, they nerfed it now. But it's like maybe the same model, and like yeah, I guess like really good benchmarks are just really important, but like I don't know if we have really good ones. So
Yeah, and that's also I find the only people who seem to really have a good handle on this and whose opinion I tend to like take seriously and trust are people who use models every day to do their work. Because that's if you're doing that, you will have a sense based on your own use cases and how complex or not they are, what is good, what is bad, which models do good, which models don't quite cut it, and when new models come out, whether they're better than other ones, because like you have a very concrete set of requirements that you're coding against, or that you're whatever work you're doing might even be just like copyright work, and it's like Claude 4.1 comes out and it's all of a sudden writes way better direct response copy. So I tend
mm,
to follow people who are just using these models on a regular basis, and when they kind of get really hyped about a new model, I'm like, okay, this model might actually be more useful and better. But then I'm also one of those people, so I don't even really particularly need anyone's opinion, because I am forming it myself based on me just using the models. Like I don't really care what people say the best model is, because I am deciding myself through my own use cases.
mm. Yeah. Some people have like, yeah, like their own little internal things that they always try the new models out on.
Mhm.
And so
I
some
like
of these
just
are,
coding up a,
yeah,
a, a front page of a website. Like you
mm,
have some copy for a thing you want to sell, you have it just create you a single index.html file and make it look good. I find that's just a really interesting task to give them.
I think I saw one from Kelsey Piper maybe that was really good about like you give it you give the model like a chess, like an endgame puzzle, of like, mate in one that actually doesn't have a mate in one, and you see whether the
Mm,
models like actually are honest with you, and they realize that this is the case. And I think it wasn't until relatively recently that models started solving this.
Interesting. I think I found their tweet about this. It says oh 04 Mini High is the first AI to pass my personal secret benchmark for hallucinations and complex reasoning. So yes, now I can tell you all what that benchmark is. It's simple. I post a complex mid-game chessboard and mate in one. The chessboard does not have a mate in one. Yeah, this is it. Let's put this in the chat. No, that's super interesting, because I'm kind of two minds with these types of things, because I think that it's really useful to find the limits of a model's capabilities, and usually that requires doing something very contrived. But I also find that the more you try and find a contrived thing it fails at, the further that gets from whether it can actually do something useful for you in the real world. You know what I mean? Because that's why I find people who work with them day to day, they have specific tasks
Yeah.
like, write this new feature for me. Either the feature works or it doesn't. That's something that's very concrete, versus like, can this thing create an image of a wine glass where the wine glass is completely full instead of just half full? Like that was the biggest challenge for image models for the longest time. And I'm like, but does that actually matter?
Yeah. I feel like, I don't know, at least like in Anthropic's marketing, they're like, we really just care about like the real world utility of the models rather than they're like,
And I think their success has borne out that strategy.
yeah, it's harder. It seems like harder to create environments for, harder to train on. Like it's pretty easy to train on like puzzles, 'cause it's easy to grade.
Right. Yeah.
Software engineering seems a little bit harder. Um,
This is such a broad problem set.
yeah, and probably there's going to be a lot of work over the next few years going into figuring out how to do RL to make the models like practically useful, not just like really good at competition math, which like they are now really good at, like with the IMO results recently and all that. But like, can you actually like replace people at their jobs? Like it seems like hard to figure out how to train the models to do something like that, but people are going to try. and I know people. It's not so.
Yeah, we can kind of start wrapping it up here with some last kind of things. Are there interesting techniques or works or research areas that people should be looking at in terms of what you just said?
As I mentioned earlier, there's a company called Mechanized. I think their essays on this topic are really good.
Cool.
There are other companies, trading environments. Yeah, I don't have that much to say. I feel pretty uncertain right now about like what the next few years are going to look like, how quickly the progress is going to happen.
You feel very uncertain, you said?
Uncertain. I don't know.
Yeah. Yeah.
Yeah.
I think that's the only really like intellectually legit way of framing it, because I think anyone there, and this is why I always have issues with people who say AGI is X numbers of months or years away, because it's like, first, you don't even have a definition of what that means, and secondly, it's like you don't know what the next 3 to 6 to 9 months are even going to look like, because the field is moving so fast.
Yeah. Yeah. It feels like AGI, at least safe the way it's saved people think about it, is just like something different than like the AI systems that we have now. This is not always super well defined, but
It's
if the
usually
thing
defined
that
as
we're doing,
what the model cannot do.
yeah, but if the thing that we're doing is scaling, I don't know, like you just scale a little bit further on a slightly more diverse set of things, and then suddenly you have AGI. I don't know if I really buy that. It feels like we're just going to add more and more diverse capabilities to the models. They're going to get more and more useful a little bit, bit by bit. Um, they are going to feed back on themselves a little bit and accelerate their own development at a certain point. But like, I don't know if we ever like, I mean, probably eventually, but I don't know really what AGI is and like when we're going to get it. Uh, Many people are
AGI
like,
is when
it's
it
just 2
can.
years, but
I was just say AGI is when it can do my taxes.
maybe that's already happened if you prompt it right, if you give it the
Oh,
right tools.
I'm sure it could do my taxes better than most tax professionals at this point. That's a
Yeah.
that's another interesting one. Real quick, is like, when will these models get to the point where just asking ChatGPT straight up will give you a better response than a doctor, versus like a doctor with ChatGPT will probably always be the best, but like a doctor who doesn't use ChatGPT, like, would ChatGPT give you a better answer? I don't know. I feel like it's probably on the margins getting there.
Mm. Yeah. Well, we'll see.
We'll see. Awesome, man. Where should people look for you on the internet?
Yeah, you can follow me on Twitter. It's Eric ERICJMICHAUD _ or if you just Google me, Eric Michaud, it's MICHAUD. I have a personal website with some of my other links.
Yeah, Google Scholar page too, and you have a less wrong account. I'm trying to find your home page. It doesn't show up very quickly on the Googles.
Oh, really?
Oh, here's that your CV does though, which is on your domain.
Oh, okay.
There's a cool site, getseo.io. You can just have it run on your site and it'll give you some SEO improvements. Maybe you're missing like a meta description or something.
Yeah, that's weird. At least when I Google my own name, my personal website just comes up first.
I'm also using Bing, so I'm not a problem.
Oh yeah, there's a bunch of other junk on here. I think maybe it's because
especially if you leave out the J,
Yeah, I think maybe at a certain point it like offered to make like a knowledge panel about me, and I
See,
sort of
this is
jumped
what
on
I was
that.
looking at. So you see here, the second one has the CV. So I clicked that and then grabbed it. Oh, bro, you're still using Arc?
Oh yeah, you can see me. Did I just share? Or...
No, I put you back on screen for a second. Don't worry, you didn't share
Gotcha.
anything weird.
Yeah, no, yeah. What did you recommend these days? What are you using?
I mean, I'm using Edge. I'm on the warpath against any Google tech, and I moved into a home with a Nest. Now I just rip it out of the wall. But
Oh
I
man.
so I don't use Chrome, and I find that Bing, it's or not Bing, Edge. It's pretty much similar. You can do vertical tabs, so that gets you kind of the arc like feel. But
Mm,
like Arc is being phased out essentially. They're moving to the new Dia thing.
yeah.
So at a certain point, you just wouldn't want to be using a browser that's not getting like I'm sure. I guess Saban is on Arc still too. That's funny. Saban, if you have any questions, hit us with it. If you actually just sat through and listened to that whole thing, then props. I think that's supposed to be greater than Dia. Got a bit lost in translation. So are you so when are you going to be done with your PhD? When are you going to become Dr. Eric Michaud?
The hope is this semester, like even sooner, like in a month, but we'll see. There's yeah, but like they
Is
said that
Max
I
on
could
your
stay both.
panel?
Yeah, it's Max, this guy Ike Schwang, and Mike Williams. So it's three physics professors. But I met with them over the summer, and they said that like anytime I could basically just staple things together into a thesis, and defend. So barring anything surprising, I should be okay.
Okay, well, sweet. Well, I look forward to whenever that is. We can have you back on so you can talk about whatever you ended up shipping as your final thesis. So that's super interesting to me. It's totally outside of my world of what I've ever done. So yeah, that would be interesting to talk about. But yeah, this has been a super fun conversation, like always. We'd love to have you back on anytime.
Great chatting. Yeah, thanks so much.
All right, and we'll catch the rest of you guys next time. I'm going to be streaming not this Friday, but the Friday after with Nikki T, and I'll be going into all the new improvements to the Auto Show CLI, which will be fun. That was one thing we didn't touch on today, multimodal stuff, which I do think would be interesting to talk about, but that is a teaser for next time. All right, bye, everyone.